Hi, I am Habibur Rahman. Now I'm going to present our paper entitled by Synthesizing Libraries of Programs with Auxiliary Functions. So let's get started. So what is program synthesis? Program synthesis is the task of automatically finding a program that satisfies the user's intent. How does a user express intent? It can be various ways like logical expression, input-output examples, natural language, partial programs, etc. So how do we define the success space? We define the success space through a domain-specific language or DSL. So the synthesizer needs the problem specification and the DSL to generate a program as output. Now, here comes our approach, auxiliary-based library learning, ALIL. ALIL learns and solves the problem at the same time. It learns the library of the programs for a specific problem. So ALIL needs a problem specification, a DSL, a domain-dependent auxiliary function, and a base synthesizer. Now let's consider this running example. We have to generate a program to process the input strings in the left box and generate the output strings in the right box. So initially, we have our DSL. And initially, our program library is empty. We then run the base synthesizer to generate some programs. Base synthesizer uses the DSL and the program library to generate some programs. We then evaluate those generated programs by our domain-dependent auxiliary function. We then check if the solution program is there or not. If we don't find the solution, we add the program with best score to the program library with cost of 1. We call it augmentation. Now we have the DSL and the program library. With the base synthesizer again, we use the base synthesizer again to generate more programs. We again evaluate the programs with our auxiliary function. Again, we check for the solution program. If we find the solution program, we exit the loop with that program. Otherwise, we select the program with best score from this iteration and add back to the program library again. We repeat the same process until we reach out to our budget or find a solution. So in the first setup experiment, we compared the base synthesizers with their augmented counterpart. We compared the algorithms in terms of the number of problems solved by the number of programs evaluated. Our auxiliary-based augmentation increased the number of problems solved by all the base synthesizers evaluated on SIGA's benchmark, often by a large margin. So in 38 benchmark, improvements are better compared to SIGA's benchmark. Here, the augmentation approach, ALIL, is never bad and sometimes superior, as you can see from the figures. So in the second set of experiment, we compared the best performing algorithms in terms of running time. So the result shows that ABASOL and AB are the best performing systems on the SIGA's benchmark, while A-cross-beam is the best performing on the 38 benchmark. So in the third set of experiment, we tried adding more than one program at a time in each iteration of ALIL. And we found that adding more programs sometimes solve more problems by a small margin. In the second variant of the third setup experiment, we tested different strength-based version of the auxiliary function. So the values of L less than 1 are the weakened versions. As you can see in the plot, with the weakened versions of the auxiliary function, all solves fewer problems. For example, an auxiliary function with 0.25 extent solves 74 problems in Segan's benchmark, and it solves 29 problems in 38 benchmark. And this result shows why the auxiliary function is so important here. If you are interested, please check out our paper for more information on OLIL. Please scan the QR code. It will link you to the paper. Thank you so much for listening.